So far, we just done one random variable, a function of a random variable, the two random variables, and the condition of random variables, a function of two random variables. And then today we are going to learn the two functions of two random variables. And every time when we learn a new type of random variable, we always want to know how do I find or express their PDF, their CDF, because the CDF is the probability, and the PDF is the density function. So either way, you find one of the function, then you can find the probability. So let's see two functions of two random variables. I have two random variables and it is jointed, distributed. We should have joint distributed random variables, and we have a joint PDF. So now I have a joint PDF. We define another two random variables, W and V. For these two random variables, it is a function of two random variables. Okay, W is a random variable, and it is a function of x and y. V is also a random variable, and it is a function of two random variables, x and y. Now I want to find the joint PDF of W and V. Okay, so how do I find this joint PDF? So one way we know that every time to get the PDF, either joint PDF or PDF, we can find the CDF first and then take the derivative of your CDF to get PDF. So here we can also find the CDF first. So let's find the CDF. W and V. So what is the CDF? That is the probability. Okay, so the probability of your random variable W less than or equal to W, certain value, intersect your random variable V less than or equal to some value V, for instance. That means my random variable x and y is in the region D. Okay, so here we can say that for any given W and V, for any given W and V, we can define what is the region D. Let's define the region D of W and V, that is your x and y, and xy is in the plane such that the function of xy is less than or equal to W, and also another function h of xy is less than or equal to V. And then since x and y are in the region, that means my joint PDF . the join PDF in the region DW, and then take the integration. And then to find the PDF, join PDF, we can take the derivative of our joined CDF. So for the joined PDF, that'll be the derivative, partial derivative of your CDF with respect to W and V. Okay, that's the typical way that you should think of, because every time when we introduce a new random variable and are trying to find the CDF or are trying to find the PDF, the first thing that pop up from your mind should be like having the CDF and then take the derivative of your CDF to get your PDF. And here we can also use another way to find the PDF. Now we assume my function g and function f, my function g and my function h satisfy those two conditions. First, w and v can be uniquely solved from x and y. And then the partial derivative, partial x over partial w, partial x over partial v, partial y over partial w, and partial y over partial v. Those partial derivatives exist and are continuous. And in this case, we can find a joint PDF of w and v. But it's kind of like a direct approach. So the PDF, the joint PDF of w and v is equal to the joint PDF of xy and times the Jacobian. And here it is, this is absolute bar. And then what is this term? The Jacobian. The Jacobian is the determinant. So this one, this time, this is a determinant. How do we find the determinant? Here the Jacobian is the partial x, partial w. First, in the first row, partial x over partial v. Second row, partial y. We need to think about y. Partial y over partial w, and partial y over partial v. And here we can get partial x over partial w, partial y over partial v, minus partial y over partial w, and partial x over partial v. And this is called the Jacobian of the transform. The Jacobian of the transformation So now, for example, let's see x and y are independent with zero mean Gaussian. So it's a Gaussian random variable, zero mean, and they have a variance sigma square. So both of them have the variance sigma square, but they are independent. And I have another random variable r. I think that's the magnitude. And the theta. Theta is arctangent y, x. Then I want to find the joint PDF of the radius and also the phase, the theta. So here we can draw the x and the y. So I have an x and y at this point. That's xy. And here is my theta and also my radius r. So now to find the joint PDF, first we know the r is the magnitude or the radius. And your theta is arctangent. And x is a function of r and theta. How do I express x? So x is here. There'll be your r cosine theta. And y will be r sine theta. So x is r cosine theta. And y is a function of r theta. That's r sine theta. So now we can, and since x equals r cosine and y equals r sine theta, we can see that the partial derivative all exist. Okay, so we can write it down. The joint PDF of r theta will be equal to the joint PDF of xy. X is a function of r theta, and y is also a function of r theta. And then I times the Jacobian, absolute value of Jacobian. And let's see the Jacobian. First row related to x, so partial x over partial r, and partial x over partial theta. Second row, partial y over partial r, and partial y over partial theta. Then you'll get cosine theta, sine theta, and then the second column minus r sine theta, and R cosine theta. In this case, we'll get R. So now this part is R. And we know that the joint PDF of xy, they're independent Gaussian. So I can separate that to f of x and f of y. So the joint PDF of x, y will be the multiplication of their individual or marginal PDF. Both are Gaussian, so it becomes, and with the zero mean and the sigma square for the variance. So 1 over 2 pi sigma square exponential minus x squared plus y squared divided by 2 sigma squared. So I can write it down the joint PDF of R and theta. Now for this joint PDF, there'll be a joint PDF of xy, that is 1 over 2 pi sigma squared e to the minus 1 over 2 sigma squared, and x squared is r squared times sine squared, and the y squared, that'll be r squared cosine squared times the Jacobian absolute value of r. Then you have r divided by 2 pi sigma squared exponential to the power minus r squared divided by 2 sigma squared. And the range for your r is greater than 0. So r is from 0 to infinity. And how about theta? Theta is from 0 to 2 pi. So this is joint PDF. Now let's see the marginal PDF of the R and also the marginal PDF of theta. So here is a note. What is the marginal PDF of the radius R? Remember, the marginal PDF, that means I don't need the other one. The other one is theta. So I don't need the other one, so I just do the integration with respect to the theta. And since theta is from 0 to 2 pi, now let's bring this joint PDF here. R over 2 pi sigma squared exponential to the power minus r squared over 2 sigma squared. And then my range for r is from 0 to infinity. D theta, that is r over sigma squared times e to the power minus r squared over 2 sigma squared. And the r is from 0 to infinity. And this PDF, let's see, this PDF is called a relay PDF. relay And how about the theta? The PDF of theta. The PDF of theta, that means I don't need the radius. So I do the integration with respect to the r. So here I have dr. And we know from the radius it is from 0 to infinity. So here 0 to infinity. And r squared, I think it should be just r. R divided by 2 pi sigma squared. Exponential to the minus r squared over 2 sigma squared. And my theta is from 0 to 2 pi. And then doing the integration, you'll get finally 1 over 2 pi. And your theta is from 0 to 2 pi. And for this distribution, you can see this is a uniform distribution. So uniform PDF. And this uniform PDF is on the interval 0 to 2 pi. Okay, next, let's see another example. X and Y again are independent, and X is Gaussian with zero mean and variance 1. Y is also Gaussian, zero mean, variance 1. And then now I want to find the PDF of W. Okay, not a joint PDF, but just PDF of W. And W is X over Y. How do we find that? You see, this is like 2 random variables and another one, a random variable. This random variable is a function of 2 random variables. Last week or last 2 weeks, we learned that if X and Y are independent, then my random variable equals X plus Y. What is the PDF? The convolution of your PDF of XY. And we also learned X times Y and X minus Y. Now, let's see, if I have X divided by Y, what should we do? How do we find the PDF? And since X divided by Y, they'll be a little bit complicated. We can also try to add another random variable to help to find the PDF of W. It is called the auxiliary random variable. We can think about W and maybe another random variable called Z. Find a joint random variable. And then PDF of W is like the marginal PDF of your joint PDF, right? So once you have a joint PDF, you take the integration, integrate the Z out, so DZ. Then you'll get the marginal PDF of W. So in this case, we assume there's W and Z. So this joint PDF is equal to the joint PDF of XY, and X is a function of WZ. Y is a function of WZ times the Jacobian, the absolute value of Jacobian. Partial XY partial WZ. Then you say that, well, since I created a new random variable Z, then what is Z? Here we can think about Z as just equal to Y. Suppose we assume that Z, random variable Z, just random variable Y. That means X, a function of WZ, will be WY or WZ. Okay, because Y equals Z, this becomes WZ. And Y function of WZ will be just Z. Then the Jacobian partial XY partial WZ. Will be partial X over partial W, partial X over partial Z. Second row, partial Y over partial W, partial Y over partial Z. This gives you partial X over partial W, we get Z. Partial X over partial Z, we get W. Partial Y over partial W, we don't have a W, so 0. Partial Y over partial Z, that's 1. So overall, the Jacobian is Z. So here is the absolute value of Z, and X and Y are independent. So here the joint PDF could be marginal PDF of X times marginal PDF of Y. Now we can find the PDF of W. So to find the PDF of W, I have a Jacobian, the absolute of Jacobian, and then the multiplication of your marginal PDF of X. And X is a function of WZ. And also the marginal PDF of Y, that's a function of Z, DZ. So here we have absolute value of Z. And for your PDF of X, that is the Gaussian with 0 mean and variance 1. So that is 1 over square root of 2 pi e to the minus x squared. X now is WZ, divided by 2. And for the PDF of Y, 1 over square root of 2 pi and exponential to the minus z squared over 2 dz. So you get 1 over 2 pi z times exponential minus 1 plus omega squared, omega w squared and z squared divided by 2 dz. And now I have two parts because I want to take the absolute value out. So I will do the integration from 0 to infinity and also minus infinity to 0. So here, I have 1 over 2 pi. First, let's see the integration from 0 to infinity. We have z times exponential minus 1 plus w squared z squared dz. And from minus infinity to infinity, I have minus sign minus 1 over 2 pi from minus infinity to 0, z e to the minus 1 plus w squared z squared over 2 dz. Then this is 1 over 2 pi. Here we have minus 1 divided by 1 plus w squared e to the minus 1 plus w squared z squared over 2. And then your z is from 0 to infinity. And the second part, minus 1 over 2 pi. Similarly, but I have a minus, similarly, we still have minus 1 divided by 1 plus w squared. And then exponential to the power minus 1 plus w squared z squared divided by 2. And the z is from minus infinity to 0. So here we have 1 over 2 pi. 1 divided by 1 plus w squared. Second term, also 1 over 2 pi times 1 divided by 1 plus w squared. So we have 1 over pi it's just 1 over pi times 1 plus w squared. In this example, we learned that we can use an auxiliary random variable to help us find our PDF. But for this auxiliary random variable, y z equals y. Why not z equals x? Or z equals x plus y? Why did I choose z equals y? And how do I know that I should choose z equals y? We know we have a formula, right? To find the joint PDF, I need the joint PDF of xy times the Jacobian. What is the Jacobian? Here. And then later on, so since I have a Jacobian, of course I want the Jacobian as simple as possible. So you can see that if I let z equals y, I can make one of the elements inside the determinant equals 0. So I can get a better Jacobian, the easier for us to find the PDF. So that's why I choose z equals y. You can also try others, okay? But the purpose and the goal is to try to make your Jacobian or your determinant as simple as possible. Okay. So in this way, I can create a 0. If you let z equals x, then also you will get 0. If z equals x, then here we have w equals x, x equals wy. And if you have z equals x, so z equals wy. And then I still get the y here. So I cannot express the x and y in terms of w and z. Okay. All right, so that is the two functions of two random variables. Now the next is, since I have two random variables, and how about three random variables or four random variables? What is the CDF and PDF? How can I express the CDF and PDF? Then we will extend our random variables. If it's more than two, then we call it a random vectors. So for the random vectors, this is the idea. We just considered one random variable and also two random variables. Then why not just 3 or 4 or even n random variables? So if I have an n random variables, now it's like this: x1, x2, x3, x to the xn. And we can collect this random variable together to have an n-dimensioned random variable. So we have an x underscore. So this is the vector. Okay. So we can think about random variables, more than 3 random variables, as a random vector. So for the random vector, I should have a joint distributed. I should have a joint distribution. So x1 to xn, we have an n joint distributed random variables, and we say that the vector, this vector is called random vector. So we'll map the random variable or random vector from our sample space to R to the n. Then what is the CDF? How do I express the CDF? So here is a random vector. Random vector. That means my joint CDF x1, x2 to xn. We define that remember for CDF is the probability. So this is the probability. Okay, and remember, how do I define the joint CDF? That means the probability, your first random variable less than or equal to some value, and intersect the second random variable less than or equal to some value. And now we have n random variables, so we need to consider all. So here, until intersect till the nth random variable less than or equal to some value. And then we can predict that the joint PDF of this random vector will be taking the derivative of your CDF. Now let's see the PDF. So as we say that to take the derivative, so here is a notation for your joint PDF as a random vector. So I have x1, x2, again until xn. So this is to take the derivative of your CDF. Partial n f and a random vector x1 to xn. Partial x1, partial x2 to partial xn. And here is a note for the probability. Your random vector in the region, that means I take since it is a probability, so, and also if I have a PDF, then that is the integration in this region D with our joint PDF. And we can write it down in the integration to the real line. And in that case, in the real line, that means I should have an indicator function in our function here. So I change the D to the real line. That means I need the indicator function to restrict the range of the X. And this is the n-fold integration from -infinity to infinity. F x, x1, x2 to xn dx1 dx2 to dxn. So this is n-fold integration. So in this case, actually we generalize our PDF and CDF, and the properties for this PDF and CDFs are the same. So all the general properties of CDFs and PDFs will generalize from 2 to n dimensions. Now let's see this example. If I have 4 random variables, x1, x2, x3, and x4. So first, what is the PDF or joint CDF of x1, x3? I have 4 random variables, and I have a joint CDF for x1 to x4. But then what is the joint CDF of x1 and x3? From the properties we just learned in the previous weeks, the properties of a CDF, to get the joint CDF of x1, x3, that means I don't have x2 and x4. So what should we do to x2 and x4? That is the CDF of x1, x2, x3, x4. And then that x2 goes to infinity. And also x4 goes to infinity. Then how about the joint PDF? x1, x3. You can also think about it, this joint PDF x1, x3 is the marginal PDF of x1, x3, because I have a joint PDF of x1 to x4. So from the joint PDF of x1 to x4, how can I get the joint PDF of x1, x3? We don't need x2 and x4, so we can take the integration with respect to x2 and x4. Okay, so now we just learned how do we express the PDF and CDF. And since remember that when we learn the random variable, x, one random variable, then next is a functional random variable, x, and then functional random variable. Now I have a random vector. I can also have a function of a random vector. Then how do I find the PDF or CDF? Here we call the transformation over random vectors. This is a random vector, and I also have another random vector. And this random vector, each random variable is a function of a random variable x. And here you can see that this j should be 1 to k. Okay. I have a random variable 1 to n. And for this transformation, it could be yk to gk. And I think, this should be k. For example, x random vector could be x1, x2, x3, x4, x5. But y will be y1, y2. Okay, so y1 will be a function of x vector. y2 is also a function of x. Then what is the CDF of y vector? So here I have n-fold. For for the CDF, that is PDF for x from x1 to xn, and then here's a region. This is a region from y1 to yn, yk. And here I have an n-fold integration. And the PDF, just take the derivative of your CDF. This is the basic way to find the general way to find your PDF. Having the CDF, take the derivative to get your PDF. Remember that we done another way, another approach called direct approach. If I have a PDFs, how can I get the PDF directly from the other PDF? Here we have, suppose for this direct approach, I need to have one-to-one mapping. So the elements of y and elements of x should be the same. Okay. But in this case, let's see this theory. Given a random vector x1 to xn, and also another random vector y1 to yn, and it is one-to-one mapping. So here you can see that y1 is a function of x1, y2 is a function of x2, y1 is a function of random vector x, y2 is a function of a random vector x, and yn is also a function of random vector x. Then the joint PDF of y, there will be the joint PDF of x times the Jacobian. And how do I express this Jacobian? First row will be always related to x1. So I have a partial x1 over partial y1, partial x1 over partial y2, till partial x1 over partial yn. Second row will be related to x2. So here you can see the OX2. Until the last one, the xn. So partial xn over partial y1, partial xn over partial y2. And then till the last element, partial xn over partial yn. Okay, so this is a direct approach. And since I have so many random variables, I may find the conditional random variables or conditional densities. So how do I express the conditional densities? This should be x2. So for the conditional densities, what is the conditional PDF of your x1 to xk? Condition on to xk plus 1 to xn. That means I have x1, x2, x3, x4, x5, and x6 or x7, for example. Now, what is the conditional PDF of your x1, x2, x3, condition to x4, x5, x6, x7. Okay, total I have n random variables, and maybe the first k random variables condition on the rest, or even I can randomly pick from like x2, x5, x6 condition on x7, x1. So just by the definition, for joint PDF, for conditional PDF, I have a joint PDF divided by another joint PDF for k plus 1 to x to the n. For example, the joint PDF of x1, x3, condition on x2. So x2 equals some value. This means I have a joint PDF of x1, x2, x3. So here's a joint PDF of x1, x2, x3 divided by the PDF of x2. Right, next, let's see the correlation and the covariance. I have a random vector. Let's just recall that the correlation between two random variables. What is the correlation of two random variables? xj and xk. So the correlation for these two should be here. Correlation jk, that is the expectation of your xj times xk, and your j is from 1 to n. Also, your k is from 1 to n. And the covariance, that's the expectation, xj minus the mean times the xk minus the mean. And again, j is from 1 to n. And k is from 1 to n. And if you really plug in the j and k, and you will see they'll be really complicated. So in this case, we would like to have it in a matrix form. So here's the matrix form. Correlation, this one. 1, 1 means that x1 times x1, the expectation of x1 times x1. R1, 2, expectation of x1 times x2. And then the covariance matrix here. Next, let's see the characteristic function of a random vector. So for the characteristic function, x is a random vector, then the definition of our characteristic function is here. I have omega 1 to omega n, and we can write it down. There's omega underscore. This is defined by expectation, exponential to the power minus I, first omega 1 times x1, and then second omega 2 times x2. This is the linear combination of your random variables, equal to, I can also write it down as expectation, exponential to the power minus I omega x transpose and omega is a row vector. Here's a note. If I have a random variable z that is equal to x1 plus x2 till xn, then if we know the characteristic function of x, then what is the characteristic function of z? This means, and if the characteristic function of x is known, so omega 1, omega 2 till omega n, this is the characteristic function of a random vector x. If, then what is the characteristic function of z? Characteristic function of z, that's expectation to the e to the minus I omega z. That's the definition. And then we know that z is x1 plus x2 till xn. So here is expectation exponential to the minus I omega x1 plus x2 plus x3 till xn. So here we have e to the I omega x1, e to the I omega x2. So it's all omega. So here you put omega 1, omega 2, omega n to all just omega. Okay, so here we have the characteristic function of x. But here we have all omega. Instead of omega 1, 2, 3, we have omega only. Then if x1 to xn are independent, then how do I simplify the characteristic function of the random variable z? So if x1 to xn are statistically independent, x1 to xn are statistically independent, then the characteristic function of z is the multiplication of x1, x2, characteristic function of x2 till the characteristic function of xn. And we can just write a product of I from 1 to n. Okay. Now let's see some examples. I have 3 random variables. So I have a joint distributed random variables with the PDF. Now I want to find the joint PDF of yz, or x given yz, or the PDF of z, or PDF of y given z. or the PDF for xy given z. So first, let's find the PDF of joint PDF of yz. Joint PDF of yz, that means I don't want x. So this is, you can think of this as a marginal PDF, but I don't want x, so I will integrate x out. So the first joint PDF of yz will be the integration of your joint PDF of xyz. But I don't need x, so I will have dx. And then let's see this PDF. I have exponential to the power square. So we can rewrite or rearrange this joint PDF. And also you can see I have 1 over square root of 2 pi. So how about just rearrange it as 1 over square root of 2 pi. Exponential. Exponential, I have minus 1/2 times x minus y divided by z squared. I have like something divided by something. Okay, some square divided by z squared, or 2z squared. So we can think of this as your variance. So we times z here. Since I times z in the denominator, I need to compensation. So here I have a z back times z. And the rest will be 3 over 3z squared over 7 and e to the minus, oh my god, that should be z. It should be z. Okay, e to the minus zy. And then your y is from 0 to infinity. And your z is from 1 to 2. And then see this part. What is this integration? This is the PDF, right? PDF of what? Gaussian PDF with mean y and variance z. And then if this is a PDF, I do the integration from minus infinity to infinity. This integration actually is equal to 1. So now I have z times e to the minus zy. And your y is from 0 to infinity. And your z is from 1 to 2. Next, what is the PDF of x given yz? So x given yz, that is the joint PDF of xyz divided by the PDF of yz. That is what we got from the previous. So here we have 1 divided by square root of 2 pi still over z. And then exponential to the power minus x minus y squared divided by 2z squared. How about the PDF of z? To find the PDF of z, we have the PDF of yz. So we can think about this as our joint distribution. And then f of z will be the marginal PDF. So I have yz, the joint PDF of yz. And since I want to find the PDF of z, so I don't want y. So I take dy, and you'll get, since y is from 0 to infinity, so here 0 to infinity, z times minus e to the minus zy dy. And then I think I missed something. Right, I still have this term. So my joint PDF of yz, here I should have still 3 divided by 7 times z squared. And z is from 1 to 2. So here I still have 3 divided by 7 times z squared, and z is from 1 to 2. Then what is this integration? You should know that for this integration, this actually is a PDF of exponential distribution. So this is exponential with the parameter 1 over z. So this integration from 0 to infinity, that will be 1 from the property of your PDF. So you get 3 over 7 times z squared and 1, 2 for the z. Next, what is the conditional PDF of y given z? That is your joint PDF of yz divided by the PDF over z. So it is from the first divided by our third result. Get z times e to the minus zy. Your y is from 0 to infinity. Last one, the PDF of xy given z. That'll be the joint PDF of xyz divided by the PDF of z. And you have 1 over square root of 2 pi times z, and the exponential to the power minus x minus y squared divided by 2z squared, and then times z times e to the minus zy, and the y is from 0 to infinity. Next is the joint Gaussian. So what is a joint Gaussian? Here is a definition. I have a two joint distributed random variables x and y. And then how do I express this joint Gaussian? I still have 1 over square root 1 over 2 pi, and then your variance times square root of 1 over r. And we'll see what r is. The correlation coefficients. And then exponential. X minus the mean squared divided by the variance squared. Also y divided by the mean squared divided by sigma squared, the variance squared. And then we have like conjugation term. X minus mean times y minus mean and divided by their multiplication of the variance. First, and also the mean is in the real line and the variance is greater than 0. And your correlation coefficient is between -1 and 1. So first, let's see. We learned that if it is uncorrelated, does that mean it is independent? Uncorrelated means the correlation coefficient is 0. Normally it is not true, right? We proved this. Let's see this joint Gaussian. For joint Gaussian, if x and y are uncorrelated, uncorrelated. So r equals 0. I don't have this term. R equals 0. I don't have that term. R equals 0. This is 1. Okay, so we can rewrite the joint PDF as 1 over 2 pi sigma x sigma y exponential for exp minus 1/2 here I have x minus the mean squared divided by 2 divided by sigma squared, the variance squared, and then y minus the mean divided by the variance squared. Then actually we can separate these two as one over 2 square root of 2 pi times variance squared of x exponential minus x minus the mean divided by 2 sigma squared. And the other one also 1 over square root of 2 pi times the variance y squared. And then exponential minus y minus mean squared divided by 2 times the square, variance squared. And this is the PDF of x times the PDF of y. And since it is your joint PDF is the multiplication of your marginal PDF, that means x and y are independent. So this only valid for joint Gaussian. So only for joint Gaussian. For other distribution, no, it is not true. So for others, when this correlation coefficient is uncorrelated, okay, if x and y are uncorrelated, that means the covariance is 0. And also that means the correlation is the multiplication of each expectation. And generally, if the correlation x, y is 0, then we just say that x and y are orthogonal. Remember that uncorrelated doesn't mean orthogonal. Uncorrelated doesn't mean orthogonal. Now let's see the joint characteristic function. Since here we define the joint Gaussian, how about the joint characteristic function of joint Gaussian? So here is the joint Gaussian for the joint characteristic function for the joint Gaussian. Okay. In this formula or equation, let's see this example and proof. If x and y are joint Gaussian, the mean for x and y, here is the mean for x and y. And I also have a variance of x and a variance of y. And also the coefficient, the correlation coefficient, y also. And y is r. Now I have another variable that's the linear combination of x and y. I would like to show that if I have a linear combination of x and y and y are joint Gaussian, then z is also a Gaussian random variable. How do we know that z is Gaussian random variable? If the random variable is Gaussian, then we know that they have the form of their PDF. Yeah, the PDF will be square root 1 over square root of 2 pi sigma squared e to the minus z minus the mean squared divided by 2 sigma z squared. If I have a PDF in this form, then I know this is Gaussian. That's one way we can think about. We can prove. And here we can also use the characteristic function to prove that. If z is a Gaussian, what is the characteristic function of z? Here's the proof. So if Z is Gaussian, then the characteristic function should be phi Z omega exponential minus I mean Z and omega times exponential minus 1/2 and their variance square and omega square. That is the characteristic function. And for the exam, that we will give you the table, okay, some basic knowledge that you should know. So sometimes you don't need to really derive it. But based on this characteristic function, let's see what is the characteristic function of Z. If I have this form, then we know that Z is Gaussian. So here I have the characteristic function of Z. By the definition, that's the expectation and exponential to the minus I omega Z. What is Z? Z is a combination of X and Y. So here we can replace Z by AX plus BY. So if I rearrange this, I have exponential to the minus I A omega X and also B omega Y. And this is the joint characteristic function of X and Y. So phi xy A omega and also B omega. Okay, and we know that we know X and Y are Gaussian, so their joint characteristic function is here. So plug in A omega instead of omega 1 and omega 2. We have exponential minus I omega A mu X plus B mu Y exponential minus 1/2 omega square sigma X square A square and then 2 the correlation coefficients A, B, sigma X, sigma Y, and then sigma Y square, B square. First, you can see A times the mean X and plus B times mean Y. This is still a scalar, and we can think of this as a mean of Z. And for the second part, this we can think of a bunch of combination as the sigma Z squared. So overall, compared to here, this is the Gaussian characteristic function. So Z is a Gaussian. So the characteristic function of Z has the form of a characteristic function, characteristic function therefore Z is Gaussian. Okay, last, if I have a D dimension joint Gaussian, and here's the PDF. Rather than 2, if I have a 3 or 4, even more, then this is the PDF. And for this covariance, sigma, there'll be a matrix. Covariance, x1, x1, there'll be a variance. Or covariance x2, x1, till covariance xd, x1. And for the diagonal elements here, okay, this is the variance. So here's the note. In the diagonal of this sigma, the covariance xi, if they are the same, so it is the variance. I from 1 to 2D.